Welcome to the deep dive. You're here, like us, to get smart, fast, and hopefully not get too lost in the weeds. Today we're looking at something new in mathematics, the Parascan-Jordan table.
Right. It's a method designed to speed up calculating powers of Jordan matrices.
And why should you care about, well, powers of Jordan matrices?
Because getting those powers right is pretty crucial for understanding dynamic systems.
Like what sort of systems?
Oh, anything from predicting stock market movements to modeling how diseases spread. Also really vital for complex computational simulations.
Okay.
And the traditional ways, they were just honestly very slow, especially for big matrices.
Yeah.
Computationally expensive.
Right, like multiplying a massive spreadsheet by itself again and again. Nobody has time for that.
Exactly.
So our mission today is to figure out how this Parascan-Jordan table basically acts as a shortcut through all that heavy number crunching.
That's the idea.
Okay, let's start with the basics then. Remind us, what exactly is a Jordan matrix?
Well, you can think of it as a kind of simplified standard format for square matrices.
A standard form.
Yeah, in linear algebra, it's called a canonical form. It's always linked to a specific eigenvalue of the original matrix. It standardizes things, makes them more predictable.
Okay, so you simplify the complex matrix into this Jordan form first. But even then, multiplying that repeatedly was the slow part.
That was the bottleneck, yes. It was still an iterative grind.
So how does this Parascan-Jordan table approach change the game?
Well, instead of that step-by-step multiplication, this table uses a prediction-based approach.
Prediction?
It involves pre-calculating certain key powers of the matrix.
Okay.
And then using specific formulas that are embedded within the table structure, it can essentially predict or calculate any other power you might need almost instantly.
Almost instantly. That sounds, well, pretty revolutionary for computation.
It's a significant speed up. Imagine knowing a plant's growth rate at key moments. You could then predict its size anytime without measuring daily. It's sort of like that.
I see. So compared to the old methods, what are the really big advantages here?
There are several key ones. First, obviously, is the reduced computational complexity. Fewer calculations.
Right. Less work for the computer.
Massively less work. Second, it maintains very high precision, which is critical.
Okay. Accurate too.
And it's applicable across different areas: numerical analysis, understanding dynamic systems, even optimizing existing algorithms that need matrix powers. And crucially, no more iterative operations.
So faster, just as accurate, maybe even more accurate sometimes, and widely usable. That's quite a package.
It is.
And this isn't just a theoretical idea, right? Has it been tested?
Oh, absolutely. It's been validated. Researchers tested it on Jordan matrices up to 100 by 100.
That's a decent size.
It is. And they compared the results directly against classical methods. The precision held up.
Any surprises?
Interestingly, yes. For the larger matrices, like the 100 by 100 ones, this method actually reduced some of the small errors you sometimes see on the off-diagonal elements with traditional methods.
Huh. So potentially more accurate for big problems.
It seems so in some aspects. And the method appears to scale well. There's no obvious theoretical limit preventing its use on even larger matrices.
Which is exactly where you need the speed boost most. Okay, so looking ahead, what's the potential? Where might this Parascan-Jordan table pop up?
Well, one really exciting avenue is integrating it with artificial intelligence.
How so?
AI could potentially learn to expand these tables dynamically. You could, in theory, handle matrices of almost unlimited size without pre-calculating everything manually.
Okay, interesting. Anywhere else?
Definitely potential in analyzing things like companion matrices. They show up in control theory and signal processing. And generally, building more sophisticated numerical models in science and engineering.
So if we boil it all down, the claim is that this Parascan-Jordan table is basically the fastest, most efficient way known right now to calculate these Jordan matrix powers.
That seems to be the conclusion from the research, yes. It represents a major acceleration for a really fundamental mathematical tool.
A tool that, as you said, underpins a lot of important work.
Precisely. In simulation, modeling, analysis, it's foundational stuff.
Right. So that brings us to our final thought for you, the listener. Think about how a breakthrough like this, seemingly deep in computational math, could actually ripple outwards. How could fundamentally changing the speed limit on certain calculations impact fields that depend heavily on massive simulations or analyzing huge data sets?
It really highlights how these, sometimes abstract seeming mathematical innovations can drive very real world progress.
Something to mull over. Thanks for diving deep with us today.